Thank you. I'll begin with a word of prayer. Dear Father, we thank you for this time we have just to study your creation, study abstract algebra. And I just pray you be with us today. Help us to, again, Lord, glorify you and what we do. And we just thank you for the weekend about to start, that we could get a little relaxation. In your name we pray, Lord Jesus. Amen. Okay, that's not entirely accurate. You have a test next Wednesday. Let's see here. All right, so we're talking about permutations and so forth. We have now made it to lecture 9. I will hopefully today explain to you a few more important facts about this. So I'll start out with something just a little bit of a review, not exactly, but just to get back in the swing of the notation. So if we have this this array, permutation, I'll do it in array notation. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So, and so this is a something in S9, right? And suppose your outputs are 4, 5, 7, 9, 1, 6, 3, 8, and 2. Let's check that. 4, 5, 7, 9, 1, 6, 3, 8, 2. Okay. Obviously, the permutation's what? It's written in, at the moment, array notation. So I want to show you how we can write it in disjoint cycle notation. Okay? In fact, what I'm about to show you, we did this before, but this is a claim that I'm going to make. I don't think I'm going to prove it carefully. I might read through the proof. Any permutation can be written as a product of disjoint cycles. Right? So what you can do is take whatever permutation you're looking at, in this case this one, and you just start with some particular number, in this case 1, right? And then you see where it goes. 1 goes to 4, right? And then 4 goes over here. 4 goes to 9. 9 goes to, 9 is here. 9 goes to 2. Let's see here. Sorry about this picture. 2 goes to 5. Then 5 goes to, let's see here. Obviously these pictures are kind of useless. 5 goes to, oh, but 1's over there. I don't have to write that again, right? And so then we finally I don't recommend these sorts of pictures. Goes back to 1. Of course, there's a better way to write this, right? You draw a circle. You go 1, 4, 9, 2, and 5. And, it's like this, right? That's another picture that illustrates the same notion. Okay? By the way, well, no, I'll focus here. And then, next, you just pick something else that's not been already covered. Right? We got 9 numbers to pick from, so something in here we haven't gotten yet. Let's say 3. We'll start with 3. Right? 3 goes to 7. And then where's 7 go? And that, okay, there we go. Of course, this is probably a better picture, right? Whatever. And then, of course, what happens? We've got 6, right? And we've got 8, which are just those particular numbers are what? They are they're not moved, right? These are fixed by this permutation. And there you have it. Just to reiterate, this is alpha equals to 1, 4, 9, 2, 5, and 3, 7. Okay. That's a so-called cycle decomposition. All right. If we say find a cycle decomposition for a permutation, what I really mean to say is, to be more precise, I should say find a disjoint cycle decomposition for the permutation. You can always do this. However, it's not always preferred. Oh, by the way, so let me just make a claim here. Theorem: any permutation sigma in Sn can be expressed as product of disjoint cycles. The proof is not much different than the example we just did. It really is just, I can't spell cycle. Start with a number, exhaust it, you have to loop back, and just keep going. Eventually you have a product of disjoint cycles. Now, there's more. I did an example like this, maybe I did, maybe I didn't. But I would point out to you, we can do something else here. 1, 4, 9, 2, 5, right? I can rewrite this if I'm interested not in disjoint cycle decomposition. I mean, it already is a disjoint cycle, okay? I can rewrite this actually as a product of two cycles in the following way. So I go 1, 5, 1, 2, 1, 9, 1, 4. If you haven't picked up on the pattern yet, it's like this. And then like that. Right? So inner, outer, and then just kind of telescope back. I mean, the first and the last, then you kind of go back. I don't know, however you want to verbalize this. That's a pretty neat trick. Of course, you can, if you don't believe me, you can try it out. Put 5 into this. Where does it go? Nowhere, nowhere, nowhere. 5 goes to 1, right? Put 2 into this. Nowhere, nowhere. 2 goes to 1. 1 goes to 5, so 2 goes to 5, and so forth. So this is a pretty snazzy trick, and you can see there's nothing particularly specific about this cycle that makes this work, right? You can easily generalize this to a K cycle. Theorem: alpha equals to A1, A2, AK, right? Then alpha can be written as product of two cycles. Now, two cycles, I keep misspelling cycles. See here, cycles. So another thing to call a two-cycle is a transposition. A transposition is a two-cycle is a transposition. The reason they're called transpositions is because a two-cycle just flips two numbers, right? That's all it does. It transposes them. What's the proof? The proof is really kind of easy here. The proof is actually by a formula. So, I mean, you could give a more careful inductive proof, but I'm just going to give it in this way for the moment. So, just what we got there, right? You can rewrite this as A1AK, A1AK minus 1, A1, A2, and that's it. To see, and then to show that they're equal, just consider the elements, right? So the proof that the left-hand side and right-hand side of the above are equal follows from case-by-case analysis. What are the cases you have to think about? I suppose in principle there are n cases, right? So this is an element of Sn, right? And what's the relation of k and n? What's the largest cycle in S3, for example? 3 cycle, right? So the relation between n and k here has to be that k is less than or equal to n, right? You can't have a 4 cycle in S3. We convinced ourselves of this yesterday. Okay, so all right, so I mean, you just put x equal to a1 and so forth. Here, I'll do one of the cases for you. Let me do a2. Alpha of a2. Right? From the definition, it should be the next thing I haven't written, right? It should be equal to a3, right? This is by definition from the left-hand side, right? But what happens when you feed in a2 into a1, ak, a1, ak minus 1, a1, a3, a1, a2. So if I take this product of transpositions, right, and I insert a2 into it, what happens? So you go, nothing happens. Oh, excuse me. How does this work? It's a product of transpositions, right? So we do first this one, then that one, and so forth. So first of all, that goes to a1, right? So let me sort of tell the story here. a2 goes to a1, and then a1 goes to what? a3. And then what happens to a3? There is no a3 in here, right? So if I write the next one just for the sake of clarity. So between a1k and a1,4, all of these transpositions have no a3, right? So the number a3 is fixed by those, and so the output is exactly that, right? So therefore, a3 is output of the right-hand side, and so forth. Now, if you're not content with this, you could, of course, replace my proof by formula with a careful induction, right? But I will go on. Unless there's a question about something. Not yet. All right. So next, I want to observe a few. Another example. Let's keep playing with transpositions. So basically, here's some kind of snazzy formulas for transpositions. Properties of 2 cycles. Some sort of sneaky observations here. First of all, and this is part of we proved a more general theorem last time, right? If I have A, B, C, D distinct, right? That means the 2-cycle AB and the 2-cycle CD are disjoint. We proved last class that disjoint cycles commute. So this is one thing we can say. If we have disjoint 2 cycles, of course they commute. Special case. Let's see here. That's point number 1. Point number 2, if we look at, say, BC, excuse me, times AB, and throughout all these formulas, I'm assuming that A, B, and C are distinct, okay? Otherwise, what I'm about to write won't make sense. You can't have a repeated number in a given cycle. that violates the definition of a cycle and also the corresponding array. It would say that the function you're talking about is double valued or more. Okay, so this you can rewrite as follows. This is actually equal to, and essentially I'm just undoing that trick. All right, so let's see here. This is really like B, A, C, I think. Right? You can try it out. If you feed A to this, A goes to C, right? Here A goes to B, then B goes to C, so A goes to C. If you feed this thing A goes, did I just say? If A goes to C, C goes to B. Wait a minute. I'm sorry. I'm an idiot. Let me try that again. A goes to C. Over here, A goes to B, but then B goes to C. So again, in total, A goes to C. If I input B, B goes to A over here. Over here, B goes to A, and then goes nowhere. So again, B goes to A. So as you can see, in all three cases, these are equal. But something else. This is the same as A, C, B, right? Because you can push B over the edge, if you like, loop it back. And then we can do the trick again and see this is the same as AB, AC. So there's another thing. We have BC, BCAB is ABAC. Or that's not what I wanted. I mean, it's fine. It's not wrong. It's just you could have also gone what? You could also go that this is equal to what? CBA, right? And so you would also get what? CACB. So you have these manipulations that we can make.
If that's the case, then wouldn't you write the first one as BCBA? Or is it fine either way? Not the unlabeled one, but like the first thing you wrote.
This?
Yeah, if you're following the pattern you have in the two other things, the ABAC and CACB, then wouldn't it, could you also write that as BCBA?
Yeah.
Okay.
Yeah, it'd probably be good to do that. We can always switch the letters or numbers in any given.
So in any given cycle, you
Yeah.
can push.
Just a second, I might have copied something down wrong. No, it's fine. Yeah. And then, of course, also, 3, we could look at this one here. We could look at AC, AB, AC, AB, and that would be the same as ABC, right? And there I am just straight up. I mean, here you're right, Audrey. I had to change it to this form to see how to use the trick over here in this example, right? True. But this one, I'm using it directly, right? So like AC, AB. So this then, using the fact that the cycles loop, right? Basically the fact that this is really A, B, C, if you want to think of it this way. Sometimes it's helpful. You could also write that starting at some point other than A, right? You could start at B, and then you'd have B, C, A. Or you could write it as what? Yeah, CAB. And then, of course, those also give you, going back and using the transposition trick, those give you what? Like this could be written also as BA, BC, and this one could be written as CB, CA. So in total, we get that this product of transpositions is equal to that product of transpositions is equal to that product of transpositions. So like, let me write it out again here. So I got AC times AB is equal to AB times BC, among other things. You can also solve for. We could solve for like for this one, for example. Suppose I wanted to solve this for BC. I could do that, right? What would BC equal to? BC would be equal to what? So multiply both sides by what? By AB on left, right? We know that AB is what? Right, every 2 cycle has order 2. Product of any transposition in itself is just the identity again. So if I multiply this by AB on both sides, on the left, what I'm left with is AB, AC, AB. So you also have formulas like this. You can rewrite a given transposition as a product of 3 of them in this way. Show you a proof of something now. I would point out at this point that it should start to be clear that if you have something like, let me just rattle off a couple of examples for you. This one's a good example. If I have 5792, I can rewrite that as a product of transpositions. What does it look like? Five 2, 5 9, 5 7. Right. Now, if you look at these manipulations we make over here, right? What do they suggest about calculations with transpositions? If you simplify transpositions, what's the kind of patterns that you see in all these? What can you say about, like this? I go with BC, right? And I replace it with AB, AC, AB, right? Of course, you've got this guy. The product of any transposition itself is just the identity, right? You got these ones, which basically are just saying you can commute them with other ones of various sorts. But if you look at all of these identities, there's one thing that unites them. You either have an even number of transpositions to start with and an even number of transpositions to end with. This is 0 transpositions, this is 2. Or you have an odd number of transpositions, 1, 3, beginning and ending. So whatever calculations you do with transpositions, the evenness or oddness of the total number of transpositions is either even or odd. It stays that way as we calculate. So that basically allows us to prove this theorem. Well, I'm going to call it a lemma. Lemma. Suppose n is greater than or equal to 2. Yeah. What about it? I just said even number of transpositions. That's not a transposition or a product of transpositions. But that also, well, since you said this, let me say, we're about to say a permutation is even if it can be formed by an even number of transpositions. And a permutation is odd if it can be formed from an odd number of transpositions. It's a somewhat curious fact, but a true thing, that if you have an odd cycle, it's an even permutation. If you have an even cycle, even numbered cycle, like a 4 cycle or a 2 cycle, it's an odd permutation. The evenness and oddness refers to the number of transpositions which form the permutation, not the cycle length. So this actually, we're going to learn soon, this is an even permutation. this is actually an odd permutation, because even an odd refers to the number of transpositions in the decomposition. Now you made me get ahead of myself. It's a good question, though. Suppose n is greater than or equal to 2, then the identity permutation is written as product of transpositions. And the number of those transpositions is even. I'm guessing I've said too much at this point, so I'm going to have to go on. Well, I'm not sure we have time for this proof. I'll start it anyway. So, you take the identity. First of all, n greater than or equal to 2, what's that do for us? That means that 1, 2 is in the set of permutations, right? So I can write 1 as 1, 2, 1, 2. Okay. So, and by the theorem I just erased, right, we can write the identity as a product of permutations, of transpositions rather, 2 cycles. So what we want to do then is suppose you've got 1 is equal to, set my notation here, A1, A2, all right, A3, A4, I think, all the way out to AL minus 1, AL. We want to show that there has to be an even number of these pairs. What would that force L to be? Even, that's not going to quite do it for us, is it? I mean, even. We want L to be an element of, I believe, 4n, right? We want it to be like a multiple of, it's got to be either 4 or 8 or so forth, right? 12, 16, that's what I'd be hoping for. We'd like to see that. So he says basically there are 4 cases of interest as you think about these, right? They're either disjoint or they fit one of those patterns over there. And it says in the first 3 cases, let me just write out here. So these cases, yes, CD, AB equals to AB, CD. The other kind of case you'd have here. So what he's working on basically is a way to manipulate the expression in such a way that we can put them in a certain order and count. It's all BC, AB. So ACAB, and the final one ABAB. So through the arguments we just went through over there, this is the same as CA, CB, and this is the same as BA, BC. So what he says here is, he says, notice the first 3 cases we can move A to the left. All right? See that? A starts here, move it to the left, right? A starts here, we move it. You know, this is also the same as what? ACCB, right? So we can move A to the left. See that? And over here, again, See that? So we've moved A to the left, right? I mean, correct? And of course the last one is the identity. And we cancel it out completely. So what he says is, suppose A is the largest number appearing among all the transpositions, all right, in that list. We can take the rightmost occurrence of A and move it to the left. As we move the A's to the left, at some point, the A's must cancel out, right? We have to end up eventually with this case, because it's the identity, right? So, if not, what would happen is you'd have 1 is equal to AB times tau with no A's in the tau, but that would contradict the fact that it's identity. So therefore we can get rid of all the occurrences of A by canceling out the transpositions in pairs, continuing in this fashion. After A is gone, pick the next smallest remaining number, and so forth and so on. Eventually we will cancel out all the transpositions. But the way the cancellations are done, what we're saying is either we remove a pair or we keep a pair, right? So the fact that this is even means it has to stay even any way you rewrite it. So that's basically the argument. Now, once we have that, and if you're not convinced, you can read Galilean, of course. He has I think a separate proof from the one I have in the notes here. One of my notes, of course, is a student of my brother who wrote this. Let's see here. So that brings us to the definition, which I had mentioned. If sigma is in Sn, and sigma is equal to gamma 1, gamma 2, gamma k, where gamma sub I are 2 cycles, then if k is even, we say sigma is even, and if k is odd, we say sigma is an odd permutation, right? In fact, while I'm at it, I should tell you that we define the sign of sigma as follows. So it's -1 for k odd. It's 1 for k even. It's the so-called sign of the permutations, either plus or -1, depending whether it's even or odd. Now, at the moment, this begs the question, how do you know that this is well-defined, right? Because I haven't proved that, we just proved that the identity is even. How do you know that any transposition, any other permutation is necessarily even or odd? Well, once you have that the identity is even, it's not that hard. Let me show you. So here's the theorem. Every sigma in Sn is either even or odd. And I'm using that in the mathematically precise sense of either or. It can't be both, okay? So here we go. Let sigma equal to a product of transpositions. We know we can. So I got A1, A2, A2L minus 1, A2L. And then we're also going to suppose that it can also be written as B1, B2, B 2k minus 1, B2k. All right. So notice then, all right. So this doesn't, I just got tricked into the thing that you guys are telling me just a second ago, like, oh, this is even, so it's an even number of permutations. That's not the case, right? This allows for it either to be even or odd, right? Depending on whether L and K are in 4n or whether they're in 2n. well, 4n plus 1. Anyway, getting to the point. So the identity is sigma inverse, right? And that sigma we can write in terms of the a's. And sigma inverse we can write in terms of the b's. I'm going to go ahead and use the extended sock shoes rule, right, which you can prove by induction if you like. So remember what happens if you've got a product and you invert it? The inverse is in opposite order, right? So this is like b2k minus 1 inverse, so forth. b1, b2 inverse, right? But I'm tired of writing. If you guys don't mind, what can I do? What's the inverse of a transposition? It's itself, right? So I can justifiably, right? So what do we got here? How many? My question is, how many transpositions are there here? There are L here, right? There are K here. So we have K plus L, right? Equals to what? The number of transpositions of the identity, right? So this must be even by our previous theorem, because that's a cycle decomposition of the identity. So L plus K has to be even. But what does that say about L and K? Right, both K and L are even, or both K and L are odd. But what's that say? That says the number of transpositions that form sigma is either even or odd, but not both. If it was both, then K plus L would be odd, which violates the identity being an even permutation. This argument's fun. This one over here is kind of a tedious thing, but that one's nice. Yeah. Okay, so you can use this sign to do things like, here's a fun fact for you. The determinant of a matrix you can define to be the sum over permutations, all right, minus 1 to the sigma, the sign of sigma, A1 sigma 1, A2 sigma 2, dot, 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 A n sigma n, where of course these are the components of the these are the coefficients of the matrix that you're calculating the determinant of, right? So that's just like a straight up formula for the determinant in terms of a sum over permutations. If you had linear with me, I don't give you this because you guys don't know what permutations are, so it seems kind of cruel to give you a definition for determinant in terms of something you don't know, right? But mathematicians tend to prefer this definition to mine. The definition I give, of course, is this one, right? So I give it a sum over indices as opposed to a sum over permutations, but they are the same thing. In the notes, I explain how to get the 2 by 2. I don't, actually it's my brother. He explains how to get the formula for the determinant of a 2 by 2 matrix from this. It's kind of cool. I'm going to go on though, because I want to have a little bit more time to discuss the theorem of Ruffini, and also to show you how to do some sample calculations. I don't run out of time here. Oh man. Well, let me get to it. So we've seen that we can take any permutation and write it as a product of disjoint cycles. And we've also seen that we can take any permutation and write it as a product of transpositions. These are both useful facts, and they both have their place. Now the theorem of Ruffini, which is actually kind of striking because this is from 1799 according to Galen, and yet reading Rotman, he says that Cayley introduced the cycle notation in 1815. So whatever Ruffini said, it wasn't quite this way. But here's what Ruffini's theorem in Galen says, at least. If you have sigma is gamma 1, gamma 2, gamma k, where gamma 1, gamma k are disjoint. All right, so you might say that this is a cycle decomposition with lengths m1, m2, mk respective. Then the order of sigma is simply the least common multiple of these lengths. Yep.
What do you mean by lengths?
Length 5, length 4, length 2, length 2. But that's a fair question. I don't think I defined that. But that's what it means. A k cycle has length k. So before I prove this theorem, actually, there's a couple of like much lower hanging fruits we should pluck from the tree. We have not done these yet. And I don't know, maybe in a different semester I would have put these in the last lecture, but here it is, lemma. No, this is going to lead to the proof, so it's a lemma. First of all, if you have a cycle, A1, A2, A J, the inverse of that cycle is the same thing, but in opposite order. It's true for a 2 cycle, it's also true for a k cycle, or in this case, a j cycle. And also, the order of a j cycle is j. If we were smarter, we could have used these last time to simplify our calculations in S3 a little bit. Right? Anyway, these are true. I invite you to prove them. These actually you could prove without too much trouble, but I'm going to focus here on Ruffini. So, to prove this, what do I need to do? Suppose you got sigma as advertised. All right? And let m equal to the least common multiple of m1 through mk, right? So we'd like to show that sigma to the m power, right, which is, by the way, gamma 1, gamma 2, gamma k to the m power, is the identity. If, first of all, these are disjoint cycles, right? So they commute, which means the laws of exponents work for us. And you can prove that this is the same as gamma 1 to the m, gamma 2 to the m, gamma k to the m, again, because they commute, because disjoint cycles commute. If we don't have commuting, we can't do that, right? A, B, if A and B don't commute, it is not true. This is false if AB is not equal to BA, all right? Danger. So I'm using the fact that these are disjoint and they commute when I write that, okay? Now what? Well, m is a multiple of m1 through mk, right? So what's that say? That says that m sub I divides m for each I. Is that right? In other words, m is a multiple of m sub I. in each case here. What's the order of the element, though? The order of gamma I is equal to mi. So what do we know about this? I mean, if you take an element in a group and you raise it to a multiple of the order of the element, it's the identity, right? So we've got identity, 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 identity. Sorry, 1, 1, 1. So that shows the order of sigma is at most m. So what should we do then to finish this here? So if you assume that sigma to the, let's say, j is equal to 1 for j less than m, all right, then what that will say is that gamma 1 to the j, gamma 2 to the j, gamma k to the j is equal to 1, which then implies that j is common multiple of m1 through mk, and j is less than the least common multiple, which of course is a contradiction, right? So therefore it has to be that the order of the permutation is exactly the least common multiple. Let's actually use this. So going back to our first example today, what's the order of alpha? Well, we don't usually write order of alpha, right? We usually do what? Order of alpha. It's the least common multiple. Are these disjoint cycles? Yes, they are. What's the length? 5, length. 2, order of alpha? 10. Okay. Any questions about this? I have an calculation example to finish for today. Suppose you have alpha is equal to 1, 2, 3, 4, and you have beta is equal to 1, 7, 4. And you want to calculate what's the order, among other things, of alpha beta. Actually, I do a bunch of calculations in this. I'm just going to calculate the order for you guys and call it a day. Oh, I forget. I'm sorry. I also should mention, if we just focus our attention on the permutations that have even, that have the sign of 1, that's called the AN. It's so-called alternating group. There's a subgroup of permutations we can study. If you just study the ones that are formed from an even number of permutations, that's actually a subgroup. You have a homework problem or two on it. It's actually not that complex. I've actually, in the notes, if you read, I have explicitly calculated A3 and A4 for you. So you can kind of get a better sense of what A sub n is as you read the notes from today. But to find the order of alpha beta, what would we want to do? I would suggest to you that we don't want to calculate it directly, right? Because that's a hassle. What'd you say?
Oh, I was about to say that.
Oh, that's what I've done in the past. But now that we have Ruffini, we can do better, right? So first of all, rewrite alpha beta as a product of disjoint cycles. How do we do that? Pick a number, 1. Where's it go? 7, right? And then 7 goes to 4. 4 goes to 1. Then 2. Where's 2 go? 3. 3 goes to 4. 4 goes to, where's 4 go to? 1, which goes to 2. Wait a minute. Oh, okay. So there we go. Disjoint cycles, right? Now I can apply Ruffini to this. So the order of alpha beta by the theorem of Ruffini, which we just proved, is the least common multiple of 2 and 3, aka 6. And we didn't have to raise it to the 6th power to figure it out. Obviously, this is useful for your homework, right? I think so. And also, you're asked some questions about AN. Do read the notes. I actually calculated. I'm so annoyed. It took me like an hour to write these out, and I didn't hardly talk about them today. Oh, well. Anyway, have a good weekend, you guys. I will shut up.